start with a carbonyl compound like 2-methylcyclohexanone. And treat that with a secondary amine. Let's use pyrrolidine this time. And catalytic HCl. Oh, molar. What might we expect the product to look like? So we're going to do the same series of steps, right? We're going to attack the amine. To generate that compound. And I'm not showing the arrows for the mechanism. And then we'll protonate. And then deprotonate. Forming the hemiaminal. Then we'll protonate to form the water leaving group. And then we'll lose water. Right. So that's showing the first 5 steps. We can go attack, protonation, 2 successive proton transfers, and the loss of the leaving group. What's the 6th step in this mechanism?
It's going to deprotonate one of those adjacent hydrogens.
It is. Which one?
I think the one with the carbon, oh my gosh, methyl group on it. It's more stable.
So the answer was yes, right? Which one? Yes, both. You're going to get that. And that'll be the major product because it's the more stable double bond. And because this reaction is all equilibrium, right, we would expect the more stable product to be the dominant product. But we will also get some of the less stable product. Because in this case, we started with an unsymmetrical carbonyl compound. It'll be about an 80-20 mixture in many cases. But we will get that mixture. If you want to use this reaction synthetically, you probably don't really want that. But fortunately for you, these are isolable stable products. That can be separated. So you can recrystallize it, maybe run polychromatography, some form of purification that's going to allow you to isolate your major product away from your minor product. So we can arrange to get a decent yield of the product that has that double bond in the more substituted position. These enamines used in synthesis to form new carbon-carbon bonds. So up to now, you formed new carbon-carbon bonds using the strongly basic Grignard reagent. This is not a strongly basic reagent, so we don't really have to worry about elimination like you would when using the organometallics. But because of the presence of that minor resonance structure that has a negative charge on the carbon, there's significant negative charge on that carbon, and it can react with an alkyl halide. And I actually should show that because we're going to do a reaction on it. So it could react with allyl chloride. This pair of electrons will push in, and that will assist this double bond in reacting with the alkyl halide. Normally, a carbon-carbon double bond is not nucleophilic enough to react with an ordinary alkyl halide. But there's a greatly increased nucleophilicity because, as I said, of that resonance structure that has the negative charge on the carbon. Right? Minor resonance structure. But as is so often true in organic chemistry, the minor resonance structure has a major impact on the reactivity. And because this is an enolate group, the SF2 reaction is actually enhanced. The difference in reactivity between allyl chloride and just plain old propyl chloride is about a 73-to-1 ratio. So we can form a new carbon-carbon bond we'll have our CH3 group. But now we put an allyl group in that alpha position. So this is a reaction at the alpha carbon. Right? We know that the carbonyl group can react at the carbonyl carbon by attack by nucleophiles. We know that it can react at the carbonyl oxygen by being protonated or by attacking other Lewis acids. But the alpha carbon is also reactive. And in this case, we're doing a reaction that forms a new carbon-carbon bond. It's quite mild. It's called the Stork enamine synthesis. And it's a reaction that allows you to alkylate positions alpha to a carbonyl group. You'll notice that that iminium salt looks a lot like that iminium salt. So it's possible then, from that iminium salt, to regenerate the carbonyl compound by simply hydrolysis in aqueous acid. To generate the carbonyl. And I convert it from condensed form to a line structure to show that allyl group. So the net effect alkylation at the alpha carbon. And if you wanted to draw it out as a synthesis, step one would be to treat it with pyrrolidine and HCl catalyst. Step two would then be to add that allyl chloride. And step 3 would be to do the acid hydrolysis. We have a separation, usually at the enamine stage. Because the enamines are often crystalline, and the corresponding carbonyl compounds are generally not. So the net reaction would look like that. And that would be a useful way of putting a second alkyl substituent on that cyclohexane ring. And it works fairly well, as long as where you want that second alkyl substituent is here at the more substituted carbon. If you want that second alkyl substituent over here at the less substituted carbon, the stored enamine synthesis isn't very effective, because at the enamine stage you get mostly the more substituted double bond. And you can't do this reaction in a non-equilibrium sense. It's always going to be equilibrium, and if it's always equilibrium, it's always going to lead to the more stable product rather than the one that's formed fastest. The mechanism for this is 5 steps, and it's just the inverse, it's the reverse of imine formation. So that iminium salt will be attacked by water, and then you do 2 successive proton transfers to get the hydrogen off the oxygen onto the nitrogen so that the amine can leave as a leaving group, right? Which is the inverse of the previous one. It's not quite exactly the inverse of the amine formation, because the leaving group leaves is the penultimate step, and forming imines, we actually did the nucleophilic attack in the first step, so you don't go through exactly the same intermediates when you hydrolyze one of those imine salts. So this is a useful synthetic method if what we want is that product. But what if what we wanted was this product? Where we actually form the new carbon-carbon bond at the less substituted side. Certainly we could use the stored enamine synthesis, but we'd only be able to get about 20% of that, because the other 80% would have been thrown away at the enamine stage. Or alternatively, right, if you don't want to separate at the enamine stage, you can actually make this mixture of carbonyl compounds and then try to separate the mixture of carbonyl compounds. So that's an alternative. And whether you choose to separate them at the enamine stage and then go on with the reaction of just the desired enamine, or run the whole reaction and then separate them with carbonyl, is going to depend largely on the differences in solubility of those 2 products at either the enamine stage or the carbonyl stage. The enamines are more likely to be solids though, so recrystallization to get them apart is an option, whereas these products are most likely going to be liquids, which means that polymer chromatography is really your only reasonable option. Maybe distillation, but high boiling things often decompose when you try to distill them. So how can we make this one instead? And the answer to that is, instead of using enamines, we will just use enolate ions. Because the alpha hydrogens are reasonably acidic, and we have these 3 acidic hydrogens, have a pK around 20 to 22, there are plenty of strong bases that we can use that will quantitatively remove that hydrogen with an equilibrium constant that's way more than 10 to the third. So we're basically taking the hydrogen off irreversibly. If we use an unhindered base, like sodium hydride, for example, we'll get a mixture of enolates where the more stable is the major product. And if we allow equilibrium to occur, the enolates can actually deprotogate each other. So even if we form this enolate initially, there's nothing to prevent this enolate from reacting with another molecule of the ketone and equilibrating to form the more stable enolate and regenerate ketone. So if we use an unhindered base or allow equilibrium to occur, we're going to get the same result we got for the enamine. We're going to get mostly the more substituted double bond. How could we generate mostly the less substituted double bond? What's the trick we usually use when we want to generate what we would refer to as the kinetic product rather than the thermodynamic product?
Base.
So this is the thermodynamic enolate. And that was the kinetic enolate, because these are the more accessible hydrogens. And your voice actually broke up, so I didn't catch exactly what you said. But I think you said the right thing.
I said that you want to use a hindered base.
Yep, a strong hindered base. And a common strong hindered base that's used for this purpose is lithium diisopropylamide. Lithium diisopropylamide is hindered enough that it's going to preferentially remove the hydrogen that's more accessible, and not this one because of the steric hindrance from the methyl group. And the other trick we usually use when we want to generate the kinetic product is we run it at a really low temperature. By running it at a really low temperature, we prevent equilibration. So once we form the kinetic enolate, it's not going to go and react with the thermodynamic enolate. It's not going to go and react with the starting ketone because it doesn't have enough energy to go over that energy barrier. You're always going to have a little bit of the more substituted. But in the case of the reaction with LDA at low temperature, you get a much more selective reaction. We'll get maybe 99% of the kinetic enolate with only 1% of the thermodynamic instead of that 80-20 mixture that we got. So low temperature and strong hindered base. What's the other strong hindered base that we used a lot in the first semester?
Triethylamine.
Triethylamine is a hindered base, but it's not a strong base. There was another strong hindered base when you saw it, you said, oh, it's probably an E2. So we did E2 elimination. And if we had an alkyl halide like that, where we had two possible directions where it could take off either of these two anti-hydrogens, and we wanted it to take off this one to generate the Hoffman product. We used LDA, right? That's one of the bases we used. What was the other one?
Is it like MBPCA or something? It starts with a little M.
MCPBA, that's an epoxidation reagent. That's a reagent we use to convert double bonds into three-member rings with oxygen or epoxides. Not hindered, by the way. MCPBA is, I mean, it's somewhat hindered, but not particularly hindered. So we use two strong hindered bases that you should still be familiar with. Potassium terpbutoxide was one of them. And lithium diisopropylamide was the other one. Potassium tertiary butoxide would react at the more accessible hydrogen to generate as the major product the less substituted alkene, or the Hoffman product. Why won't potassium terpbutoxide work for this reaction? It has to be LDA. So not just any hindered base, right? It's got to be a really strong hindered base. And the reason is because the conjugate acid of LDA has a pKa that's about 36, whereas the conjugate acid of potassium terpbutoxide has a pKa that's about 18. So if you were to do this same reaction with potassium terpbutoxide, generate the enolate, it would certainly generate this enolate initially, and butanol. But what would the equilibrium constant be for that reaction? I'm going to ask you the same question for this one. What will the equilibrium constant be for this reaction? Keeping in mind, right, that the pKa of this hydrogen is on the order of 20. Remember how to do that calculation?
2.
What's that?
10 to the minus 2.
So in this case, the equilibrium constant is 10 to the minus 2, because this is actually a slightly more acidic hydrogen than that one. So you can't prevent equilibrium, right? The equilibrium actually lies towards the starting material. In order to get the kinetic enolate and have it stay as a kinetic enolate, we need to run this reaction under non-equilibrium conditions, which we need a base that's much stronger than the enolate. What's the equilibrium constant for this reaction? And you'll notice I didn't write it as a reversible reaction, because it effectively isn't.
Like 10 to the 16, but that seems too big.
Yeah, it's huge. Right? So that equilibrium constant is 10 to the 16. So there's no way that's reversing. It's a really strong and hindered base. T-butoxide is simply not a strong enough base to deprotonate this in an irreversible manner at the temperature of minus 78. Whereas LDA at minus 78, this is still going quantitatively very quickly to generate this enolate, And because that reaction is not reversible, we don't get an equilibrium happening between the two. Right? So if we want a kinetic product, we want to make sure it's not under equilibrium conditions by using a strong hindered base. Once we have this enolate, right, the enolate ion reacts very readily with alkyl halides. So we can take this enolate and we can alkylate it with any unhindered alkyl halide, right? If you use a hindered alkyl halide, sometimes you get some elimination because this is it's a decent base. But if we use something like bromopropane, right, we get a nice SN2 reaction. Show it with the hydrogens. And we get a nice SN2 reaction where that enolate attacks, and we get a new carbon-carbon bond. And in this case, our major product would be the propylation, or the alkylation at the less substituted end. As long as we keep it cold, right? So we keep it cold at minus 78, and we also have to control the order of addition. We want to make sure that our enolate ion sees this before it sees this product. Right? So we got to keep the concentration of this high and the concentration of that relatively low. So we need to add the enolate gradually to a solution of the bromide rather than the other way around. Right? You can't make the enolate and then say, oh, now let me drip the bromide in slowly. Because if I drip the bromide in slowly, I'm going to get this product. There's still going to be a lot of enolate present, and we can start getting some equilibration. So the order of addition becomes important. But you can alkylate using enolate ions at the less substituted position. So if you were to do this synthetically, what time is it? So I have 1 minute. So if I were to do this synthetically, I would write out a slightly different three-step mechanism. In step 1, I'd use LDA in an inert solvent. That would make the enolate. In step 2, I would add my bromopropane. And then in step 3, I would have the aqueous acid workup, which would protonate the resulting intermediate and get rid of the strong base. And the result of that three-step pathway would primarily be the product where the alkyl group is attached to the less substituted side of the carbonyl instead of the more substituted side. So, who speaks lever fluently? What's the quiz going to be on Tuesday?
Is it the mechanism again?
Nope, you don't speak lever that fluently, I guess. We had a reactions quiz for our first quiz and a mechanism quiz for our second one.
What is this?
Synthesis. Right? So we've talked about 3 different kinds of synthesis. We talked about using those acetal protecting groups in order to do a synthesis somewhere else in the molecule of the carbonyl compound. That was the tail end of last class. And we just talked about synthesis using enolates to generate the kinetic product, and synthesis using enamines, historic enamine synthesis, to generate the thermodynamic product. You should make sure you know how to do those various syntheses, and the quiz will be synthetic related. So you won't have to show mechanisms, you'll have to write out a sequence of reactions and intermediates that generates the product. Make sense? And we are done. So I'm here for questions if there are any questions on what I've talked about, or anything else for that matter, or if you just want to vent, feel free. Any other questions? Or lab, if anyone has questions on pre-lab, I can address those too. I'm going to stop the recording and save it before I lose it.